Graeme, I've got a silly question. What happens if you have multi-phases, more than two phases?
Oh, good question. Yeah, that is a very tricky question. I mean, it's not just multi-phases, but also if you want to go beyond quasistatics. I mean, they're all challenging problems. Basically, if you're going to use these techniques, you actually have to use analytic functions of several complex variables. And the main difficulty there is that, so now instead of having a measure on the real line, you've got a measure on the plane, or, you know, a measure which is a function of not lambda, but of lambda 1, lambda 2. And the measure has to be positive. That's quite nice. But what's more tricky is the measure has to satisfy some Fourier constraints. And one of the things in the single variable case is, you know, the extreme measures correspond to delta functions. In the multivariable case, it's an open problem, and a very difficult problem is to characterize all possible extremal measures. You can get examples, but to characterize them all is very difficult. And so the most success for multivariable cases has been using the variational principle approach. That seems to be better addressed to that. And in particular for viscoelasticity, myself and Leonard Gibiansky and Jim Bergman actually obtained bounds on the complex bulk modulus, complex shear modulus, as a function of the bulk and shear modulus of the different phases. And for the bulk modulus, everything again turned out to be just simple arcs in the complex plane. But anyway, things are sort of easy to do using the variational principles. But the catch there is that in the time domain, it seems to be not so easy using variational principles. There is a paper that, or Ornella in her thesis with Angelo Carini, did obtain variational principles in the time domain. In fact, it seems very difficult to get bounds at specific times, like we obtain using the analytic approach. Anyway, that was a long answer.
I'd like to ask a question. Can I? Do you hear me?
I guess I can. Yeah, I guess you come to David. I can hear you.
Yes, my question has to do with the last part of your talk. I understand that by looking at the time dependence of various elastic or viscous behaviors of a composite, and by adjusting the boundary conditions, you can obtain information about the volume fractions of the various constituents. Are there other properties? You mentioned that there are also other properties that you can get information on or bounds on from measuring the time dependence of those processes.
That's correct. Yeah. I mean, in particular, I said that, I mean, one thing you can do, and I gave the example, is determine the response at one frequency from an input signal that doesn't involve that frequency at all. So, for example, you may want a constant frequency response, a real frequency, but you won't want to use an input signal that's only on for a short amount of time. And so this tells you a way of doing that. And then a second application would be to determine the shape of an inclusion inside a body. And in that case, you actually have to adjust the boundary fields in an appropriate way as to sort of extract that information.
Okay, thank you.
You're welcome. Other questions? There's a lot of information there.
We can't hear you, Muammer. Allô, allô?
I have another question.
Good.
Yeah.
I think all the bounds that you showed us, they are referring to linear response of the system, either electromagnetic or elastic or viscoelastic. Is there any, have you or has anyone else made progress in finding bounds for nonlinear response, either weakly nonlinear response or strong nonlinear response?
Yeah, and that's a good question. Yeah, so there's in the nonlinear response of, I'm sure you're familiar with it, of static problems like there's a approach of bounding the energy that John Willis and Talbot and Ponicastnado, a lot of people. But then from an experimental viewpoint, what you may alternatively want to bound is the relationship between the current, the macroscopic current, the average current, and the average electric field. You know, what possible pairs can you actually have? And so myself and Sergei Surkov had addressed that problem. That was again for the case where the fields are real valued, but there was actually sort of using this Gibbiansky-Shikaev trick. There's nothing preventing one to do that for the constant. I get, you know, I have to be a little bit careful because I guess if it's constant frequency, then it's a yeah, I guess that's maybe the variational principle wouldn't work because it's nonlinear. Anyway, I guess that's something to think about. And but anyway, I'm just saying there are works in that regard in the static case, but not in the dynamic case, and that would be interesting.
Thank you.
Well,
Could you comment on bonds for sign shifting media? For sign shifting media, when you allow for positive and negative real values.
Yeah, so that's when the permittivity has a, I'm just plugging in my computer. Sorry. Yeah. What? Yeah. So sometimes the bounds extend to sign varying materials. I mean, generally, if one's exactly at resonance, then the bounds are useless, basically. And so there's sort of lens-shaped regions blow up to a very large region. I mean, it can be the case that one phase has a positive imaginary part and the other phase has negative imaginary part. So one phase is absorbing and one phase is active, you know. But in the two-phase composite, what's important is the ratio between the two. And so if the ratio of the two is not real, then the bounds actually apply. So the bounds will actually apply to materials with a mixture of one phase having loss and the other phase having gain. Yeah. But not at resonance. Any other questions?
I've got another silly question. What happens if you now have bi-anisotropic media? So you know you have this system of constitutive equations which couple the electric and magnetic field, you know, via this coupling tensor, magneto-optic tensor.
Right, yeah.
Can you generalize it?
Yeah, I mean, everything generalizes. I mean, again, you can sort of, I mean, again, it's sort of the problem that you have now more variables, you know? And you know, it's the same as with dynamics. But even within quasistatics, when you have this, not just epsilon and mu, but you have this sort of coupling. Again, you're sort of dealing with functions of many complex variables. And so the analytic approach is maybe not the best. The variational approach will go through in a straightforward way. And yeah.
And you would not expect any interesting new effects. It would be just dull. Or you could...
Yeah, I mean, part of the problem, I mean, you're sort of partly addressing here is the case of you want not just quasistatics part and then sort of dynamics. And in that case, it's perhaps more appropriate to look at the response of a body or scattering of scattering of things. And so then one has to be a little bit careful. Quite fairly recently, I looked at bounds for scattering problems and variational principles for scattering problems at General Kubianski things. And I was sort of hoping to get bounds on the absorption cross-section that generalize some very nice bounds that Owen and Johnson collaborators got. This is going beyond quasistatics. And so that's related to the forward scattering amplitude. But the strange thing was, unless I made a mistake, that the bounds actually ended up for the backward scattering amplitude. So anyway, so the variational principles turned out to give interesting bounds, but not the bounds that are primary of importance anyway. Yeah. So there's still a lot to be done in this sort of general area, particularly in the case of waves beyond quasistatics. These sort of analytic properties they sort of extend to wave equations as well. I guess David's giving some talk on that. There's also in my book, Extending the Theory of, or our book, Extending the Theory of Composite, there is a science that Max Sense and Aaron Walters and myself proved this sort of analyticity of the response as a function of the dielectric constants of the body and magnetic permeabilities of the body.
And then what would you expect for parabolic equations?
Okay.
Phenomena, just like that, you know, just.
Yeah. Yeah. Well, I mean, I'm sure one will have these sort of analytic properties and things, but yeah, and I mean, parabolic equations can certainly be put in that sort of framework, what I call the abstract theory of composites. And again, that book and my research as an archive show how many different equations of physics can be fit within this general scheme of the abstract theory of composites, which then gives you variational principles and analytic properties and things. So, yeah.
Okay, thanks, Graeme, for your answers and for the presentation. Do we have let's say, a last question from? No, the audience is over. So thanks again for the nice talk. It has been recorded by Bogdan. It will be available very soon on the web page. And it's my pleasure also to use this opportunity to say that the next speaker is David Bergman. I don't know if you can hear me properly. I have a lot of echo on. Yeah. And yeah, thanks, Graeme. And then we continue the next week.
Thank you, and thanks for everyone's patience with the problem.
Thank you very much, and sorry for the disagreement in the beginning.
No problem. Everyone.
Have a nice week. Bye.
Stay safe.